Hey class, welcome back to Behavioral Statistics. We are moving into chapter 9. We're going to be looking at more hypothesis testing, but now we're going to be looking at that through the lens of t-statistic, and we'll be looking at different variations of t-statistic for the next three chapters, but this is kind of the table setting introductory chapter. So by the time this is over, this chapter, you should know when to use a Z statistic instead of a Z score. I refer to them sometimes as a Z of X bar, but Z score is fine. I might use those two terms interchangeably, but there's kind of a time and place for when you use a T statistic, time and place for when you use that Z score for hypothesis testing. You'll learn how to perform hypothesis tests using T statistics and also evaluate the effect size using Cohen's d, and also percentage of variance accounted for using R squared, and also confidence intervals. Some of the information or tools that you'll be using from previous chapters: sample standard deviation from chapter 4, degrees of freedom from chapter 4, standard error from chapter 7, and hypothesis testing from chapter 8. Really, there's shouldn't be a lot of things that are unfamiliar in this chapter. It's just a new way of framing it and kind of new conditions by which, when we're conducting hypothesis testing. So some of some of the table setting stuff we're going to be talking about. The T statistic is your alternative to Z, the Z of X bar, or the Z score statistic. Some of the items we would normally use if we're calculating Z, we would have our sample mean to estimate and approximate the population mean, and then we would have standard error on our denominator, describing how much of the difference there is between our sample mean and our population mean. And these are a couple of the formulas, different ways of conceptualizing that formula, for understanding that standard error that you would use in the denominator. So, just a reminder of what that Z-score, the statistic, looks like. If we want to calculate Z, we look for the difference between our data and our hypothesis, and then we divide that by the standard distance between those two, that standard error from the previous slide. And we can then use our unit normal table to find the critical region for our Z-scores for a normal distribution if we have our n of our sample size is over 30, and also, or excuse me, or if the original distribution is approximately normally distributed. So those are kind of the conditions in the formula for using a Z-test. There's some problems though, like it's not always applicable. It's not always appropriate to use a Z test or Z scores because sometimes they have more information than researchers actually have available to them. It's kind of assuming that the researchers have all of this particular information available, certain data that may or not be available. It requires knowledge of the population standard deviation, which is then used for computing that standard error, the numerator of our equation. And then researchers usually only have the sample data available. So in this case, we have to start kind of we have to do some different statistical procedures to kind of make up for that lack of information. So the t-test or t-statistic is an alternative, or it's kind of like an approximation to Z. Instead of using that population standard error, we're going to use an estimated standard error S subscript M, and that's used for estimating the actual standard error when that value is unknown. So we're now talking about conducting a hypothesis test on one of our critical pieces of information is unknown. So we're computing that standard deviation, computing it from the sample variance or the sample standard deviation, and it gives us an estimate of the standard distance between our sample mean and our population mean. We're again kind of looking for those approximations. And so, in order to find that estimated standard error, you can see it depicted as S squared or standard deviation squared. The formula here, estimated S subscript M equals S. That's going to be your variance divided by the square root of n being your sample size. So when the value of that standard error is unknown, we use the estimated standard error. We use this instead, and it is the variance. It's a unbiased statistic. We've talked about biased versus unbiased statistics in previous chapters. So the t statistic, essentially, the formula for our t-test is this here. Same numerator as our z of x bar test, but now instead of our standard error of the mean, we're going to be looking at the estimated standard error, which is just this equation here. So another way of putting that, I think I have another depiction later on. I'll show you. But the t-test is used for testing hypotheses about an unknown population mean when the value of the standard deviation is also unknown. So we're venturing into the unknown. We're making inferences, now venturing into the unknown. So wading into the waters of inferential statistics. So what it and now you're going to use instead of the normal distribution chart, you're going to use the T distribution chart. If you're on Moodle, if you're watching this, in the class that we're running through Moodle, you should have access to that. There should be some tables that are provided to you, but you're instead of looking up those critical values ahead of time, the critical values are going to be determined by your sample size and then also your degrees of freedom. So that's how you're going to use that chart, depending on are you using a one-tailed test or a two-tailed test, how big is your sample size, and then you also look at degrees of freedom and your critical value. So sample variance requires the computation of our sample mean first. We're going to use n minus 1 to represent n being our sample size minus one, all of our samples that are independent, meaning they're free to vary. Researchers call these degrees of freedom. It's describing the number of scores in a sample that are independent and free to vary. In the t-test, these are basically the number of values in your data that are free to vary when estimating a statistic, kind of like the mean. You'll typically see these depicted as df, lowercase df, and then you'll see it n minus 1. We'll have number of our sample size minus 1. So this is just a quick just refresher. When do we use the z of x bar? When we know our sample mean, when we know the mean population and standard deviation. If we don't know those things, we have to generate estimates, and those estimates are when we use a t-test or we use a one sample t-test. So when you're comparing a sample mean to a population mean, if the mean is known, standard deviation is unknown, we can use t-test instead, and we can establish either a two-tailed test or a one-tailed test and the critical values for those. And so this is the equation. Like if you were taking notes, or if you're having maybe some notes handy while you're working on your homework, I would have this equation somewhere. You can see it pretty regularly because you're going to be using this for most of your homework for chapter 9. So the t distribution, similar to a normal distribution, it's a family of distributions. There's, one for each possible number of degrees of freedom. So in theory, you have some for degrees of freedom for 20, for 5, and kind of everything, in between. And really what it's trying to do is approximate. Remember, this is an approximation of a z of x bar test. So it's going to try to approximate the shape of a normal z-score distribution. However, it tends to be flatter than a normal distribution. The spread is a little more out than the z-score distribution. There tends to be more variability, meaning there's fatter tails at the end, and then that's affected by the degrees of freedom. So the longer the larger that number is for degrees of freedom, the more likely it is to start to resemble a normal distribution or that z-score distribution. So notice when it's degrees of freedom are 5, it's a little bit flatter. The tails are a little bit thicker on the end. When it goes to 20, it's a little more peaked. More of our data is kind of being collected in the middle. The tails are getting skinnier, and then the normal distribution itself. So once it gets closer to 30, we start to look more and more like a normal distribution. So this would be a normal distribution with a t distribution, or excuse me, t distribution, degrees of freedom of 3. We have our critical values of negative 2.353 on the left-hand side, positive 2.5353 on the right-hand side. Any values, when we compute that t statistic using the formula I just showed you, any values that fall into either of these darkened areas means we reject the null hypothesis. So here's our equation again for conducting a t-test for a one sample t-test. And if we assume that our null hypothesis is true, we would get a value of zero. Essentially, we're saying there is no difference between our sample mean and our population mean. There's no statistically significant difference between those two. But again, we're collecting data. We have some information about the population before the treatment. We conduct our research. Maybe it's a new form of therapy. Maybe it's an educational intervention. Maybe it's a new medication for, depression, whatever it is. We have that treatment. Then we calculate our statistics from this population unknown after the treatment. And we want to compare and see, okay, is there a significant difference before treatment versus after treatment? And just like our Z of X bar test we did in last chapter, you're going to conduct 4 steps to conduct hypothesis testing. One, you're going to state the null and alternative hypotheses and select your alpha level. Typically we're talking about an alpha level of 0.05. In the social sciences that's very standard. You obviously can increase or decrease alpha if you want, but typically the rule is 0.05. You're going to locate the critical region using the T distribution table and value for degrees of freedom. So again, if you're taking this class through Moodle, you can go into the class section and you should be able to find a section for tables and charts that you can download, or you can just Google T distribution table and you'll probably find exactly what we're using. So either way, you can find it. You're going to calculate the T statistic using that formula provided and then make a decision regarding the null hypothesis. Do we reject the null hypothesis or do we fail to reject the null hypothesis? So our rejection regions, again, are going to be in these tails, and it's determined by our alpha level. It's also determined by our degrees of freedom. So you would go and look at the T distribution for an alpha level of 0.05, degrees of freedom 8, and that would give you these two critical values on the left and right hand side. Anything that falls in between, we fail to reject the null hypothesis. So some of the assumptions based around our t-test, the values in the sample must consist of independent observation, which just means each data point in our sample does not influence or depend on any other data point. The population sample must be normally distributed. When that sample size is relatively large, we can get away with violating that assumption without affecting the validity of our hypothesis test. The larger the sample, the smaller the error. The larger the variance, the larger the error. The larger the variance also means that you're less likely to obtain a significant treatment effect, and that reduces the likelihood of rejecting the null hypothesis. So you can kind of see how some of these things like sample size, how does it relate to error? How does error relate to variance? How does variance relate to our results being significant or not? Kind of all of these things that we've talked about previously, how they're all tying into hypothesis testing. So let's do a quick learning check. When n is small, so less than 30, the t distribution is what? Is it A, almost identical in shape to the normal z distribution? B is flatter and more spread out than the normal z distribution? C is taller and narrower than the normal z distribution? Or D cannot be specified, making hypothesis tests impossible? Pause the video here. Make sure you understand before moving forward. You can unpause when you've jotted your answer down, maybe keep a mental note or put it down in your notes somewhere, but make sure you understand before moving forward. Okay, we're back. The correct answer in this case is going to be B. It's going to be flatter. The smaller that n is, the more flat it's going to be less peaked in the middle. It's going to be thicker on the ends. It's going to get flatter the smaller the n, our sample size is. Next one, true or false. And first one is true or false. By chance, two samples selected from the same population have the same size, sample size in this case of 36, and the same mean of 83. That means they will also have the same t statistic. Is that true or is that false? Second one, true or false, compared to a z-score, a hypothesis test with a t statistic requires less information about the population. So go ahead and mark down for both of these if you think they're true or false. Pause the video here, maybe have them, in front of you. You can pause it. Make sure you understand why it's true or why it's false before moving forward. All right, here are the answers. Hopefully you've unpaused. Hopefully you paused, now unpaused. It's going to be false for the first one. The two values are unlikely to be the same. Variance estimates, so S squared, differ between our samples. So even though they might have the same sample size, same mean, they might have different variances. Chances are they do. And then the second option, or second one is true. The t statistic does not require the population standard deviation. However, our z-test does. All right, so we can also measure effect size. I think we covered this last chapter as well, measuring effect size, not only wanting to see if there is a significant effect, but we want to see if what the size of that effect is. So hypothesis testing determines whether the treatment has an effect greater than chance. Like, or is there actually something going on with our intervention? In this case, chance is measured by our standard error, and there's no measure of size of the effect is included. Very small treatment effect can still be statistically significant. So not only do we want to know the context of whether it's significant or not, but we want to know also what are the effect size, like how big of an effect is taking place, with our significant difference. So this is when you can use your results from your hypothesis test in reporting effect size in Cohen's d, which here is the estimated Cohen's d. You take your mean difference divided by sample standard deviation. So our original equation included population parameters. However, the population mean and treatment of standard deviation are both unknown. So estimated Cohen's d is using the sample standard deviation instead. So you're going to use your mean minus your population mean divided by sample standard deviation. And so we can kind of see, what's going on with our sample distribution. What are the spread of the scores? Not only is the spread significant, but we can also see, where the magnitude of that spread. We can also measure the percentage of variance using R squared. This is an alternative method for measuring effect size. Instead of Cohen's d, you can use effect size, and then this is just called R squared. You take your variability accounted for, which is just t squared divided by the total variability. So that's going to be t squared plus degrees of freedom, your sample size. And you'll measure that. If it's 0.01, it's considered a small effect. 0.09 medium effect. Anything larger than 0.25 is considered a large effect. So you have a couple of different ways to kind of achieve the same ends. But we can take a look at and see not only is our results significant, are the differences significant, but to what magnitude are those significant, or to what magnitude can we see that the significant difference? There's also this thing we want to include called confidence intervals, really, which allow us to estimate kind of a range of values where our data might fall when we're talking about unknown values. So this is another way of describing our effect size. It's estimating our mean from the sample mean, or population mean from the sample mean. It's really based on our reasonable assumption that our sample mean should be pretty close to our population mean. It should be an approximation, should be near. And we're saying near is based on what our estimated standard error of the mean is. So that numerator we used previously for our t statistic. And what we're trying to essentially say is we can confidently estimate that our population mean should be located within an interval. It's not going to be a singular value, but an interval near the statistic. And so we can compute that. Every sample has a mean corresponding t-value with that equation. So this is just the equation we used earlier. You can rearrange that to solve for our mean. So you're just taking the same information. If we know four pieces of this information, but we don't know the mean, we can use that to find our population mean. And in any t distribution, the values will pile up around t equals 0, which is the mean right in the center. For our alpha value, we know that 1 minus alpha is the proportion that t falls between plus or minus. So again, when we use when we use an alpha level of 0.05, what we're talking about to find out our confidence interval is going to be 1 minus alpha. So our confidence interval is going to be 95%. So here's an example. If we have degrees of freedom of 8, our confidence interval is equal 95. T values fall between plus or minus 2.306 from that T distribution table. Again, refer back to the distribution. So what we can say is we can be 95% confident that a sample mean corresponds to a T value within that particular interval. So within this interval, we're 95% confident the interval would fall somewhere between here. So computing or constructing your confidence interval, sample mean, your standard error of the mean, or your estimated standard error of the mean. So you can pick an appropriate degree of confidence. You can do 80%, 90. Typically, I'd see at 95 is kind of like 0.05 is the rule, is kind of the standard for your alpha level. 95% confidence interval tends to be the value you see most often in the social sciences. And then you're using that to kind of establish your critical values. We can solve our equation. So here's just an example of a t distribution table. Find the value of t, degree equals 9, alpha level point 10, and then we have a t equals 1.83. That would be the outcome of our equation. We could then go and plug that in, solve the rearranged equation. We can plug in our mean plus or minus 1.833, and that's going to give us that range of values on both sides, a confidence interval centered around the mean, 95% confident that the population mean is going to fall one side or the other. Our confidence level, when we have when more confidence is desired, we're going to increase the width of our confidence interval. When less confidence is acceptable, we're going to decrease, excuse me, that interval. Our sample size, our larger sample, smaller standard error tends to be a smaller interval. A small sample, large standard error ends up being a larger confident interval. So just kind of showing you the relationship between sample size and confidence intervals. In terms of reporting the results of a t-test, typically you'll report whether it's significant or not. If it's significant, that means we are rejecting the null hypothesis. Not significant means we are failing to reject the null hypothesis. Typically, you'll see it reported, the t-statistic, you'll see the degrees of freedom. So it would be t, the degrees of freedom, and that parentheses equals, and then the value you get from the t-statistic. And then you can then report the significant level. P is less than alpha, or you might actually put the actual probability value. So if, let's say you got 0.029, you would say, that's obviously less than 0.05, so we can reject the null hypothesis there as well. Non-directional tests tend to be the more commonly used for our one sample t-test, our one-tailed t-test. You can use directional hypotheses, though, depending on the research situation, depending on the questions you're trying to answer. Either way, you would still conduct those same four steps for hypothesis testing, establishing your critical regions, and then conducting a test to go from there. So your one sample test, again, you would just look at a different portion of the chart of that t statistic. And so if you're looking at values on the left-hand side, they're going to be negative. If you're looking at positive values, they're going to be on the right-hand side. Okay, let's do a quick comprehension check. The results of a hypothesis test are reported as follows. T21 equals 2.38 and P is less than 0.05. What was the statistical decision and how big was the sample? The null hypothesis was rejected using a sample of N equals 21. B, the null hypothesis was rejected using a sample of N equals 22. C, the null hypothesis was not rejected using a sample of N equals 21. Or D, the null hypothesis was not rejected using a sample of N equals 22. So make sure you understand, pause the video here, jot your answer down, and make sure you understand why before moving forward. Okay, the correct answer in this case is B. We are going to reject the null hypothesis. Our p-value is less than 0.05, so we know that. And we know our N is going to equal 22 because when we talk about degrees of freedom, it's N minus 1. N minus 1. So if you see 21 here, our sample size was just one size larger. Okay, another true or false set. True or false sample size has a great influence on measures of effect size. And then second one, true or false, when the value of the t statistic is near 0, the null hypothesis should be rejected. So go ahead and pause the video here. Make sure you understand which each one of these is asking in true or false. And unpause the video when you feel like you have your answers ready. Okay, hopefully you're back. First one is false. Measures of effect size are not influenced to any great extent by sample size. That's kind of one of the convenience things about these measures. They're not influenced by sample size. And then the second option also is false when the value of t is near zero. The difference between our mean and our population, our sample mean, is also near zero. Okay, so here is a quick practice problem to kind of close things out, and then we'll probably call it good for today, to show you what this hypothesis testing might look like in establishing confidence intervals, what those things might look like in a real world situation. So you can just kind of follow along, and you can pause the video as needed, and obviously send questions if you have them. But here goes. We have a manufacturer of light bulbs claims that its light bulbs have a mean life of 1,520 hours. A random sample of 40 such bulbs is selected for testing. If the sample produces a mean value of 1,493 hours and a standard deviation of 85 hours, is there a sufficient evidence? Is there sufficient evidence, excuse me, to claim that the mean life is significantly less than the manufacturer's claim using the alpha level of zero point zero 0.05 significance level? State the hypotheses, report the test statistic, and draw the appropriate conclusion. So we're going to just kind of walk through those first four steps using all of the information we have in this paragraph. So the first thing is we want to establish our research questions. Our null hypothesis will always be there's really no difference. So if we're comparing the mean life of our light bulbs, of our sample light bulbs to our population, we're saying it's equal to. Then it's either equal to or even better in this case than the actual manufacturer's claim. Our alternative in this case is going to be a one-tailed hypothesis. The mean life of the light bulbs is less. Now, that is when we see words like less, we're talking about a directional hypothesis. And this is where it would be a good habit to get in and draw a normal distribution. And you can even draw in some of the information like the mean, the standard deviation, and also what side of the graph you're going to be working on. So directional, it's going to be a one-tailed test, and we're talking about a lower-tailed test. We're comparing the sample mean to the population mean, and we have an unknown population standard deviation, so therefore we use a one-sample t-test. And here's what that would look like. You're going to focus on the left-hand side. Your critical value is going to be here on the left-hand side. So any values that fall in this darkened area means we would reject the null hypothesis. Any numbers from our t statistic that fall here, we fail to reject. Okay, in this case, in order to determine, all you have to do is you're going to go to your t statistic. I already have the critical value here. It's negative 1.69. You would just go to the value. You would look up one-tailed. You want to make sure you're looking at the one-tailed column. You're also going to look for the column. I don't think you'll find one that says 39, so you're going to want to find the one that says 40, which is the next closest one. And our alpha level is 0.05, so you should be able to find that value. Now, I think this one is rounded, so your value might look slightly off, but it should be within that kind of same ballpark area. So anyways, this is a T critical value, not a Z critical value. So keep that in mind. This is one you have to go and look for. It's not the Z values we already know ahead of time, but these are going to be different each time depending on your degrees of freedom. Okay, and here's our equation. So we have our equation for conducting our t-test. You're just going to plug in all the information from this paragraph into here to solve. So we have 1,493 minus 1,520 divided by 85 divided by the square root of 40. That's all the information just pulled from here. We're going to get negative 27 divided by 85 divided by 6.32. That simplifies down to negative 27 divided by 13.45. That gives us a value of negative 2.007. So our critical value is negative 1.69. Our t statistic comes up with a value of negative 2.07, 007, excuse me. So we are somewhere in here. That means we are going to reject the null hypothesis. Our conclusion is the light bulbs seem to have a significantly lower mean life than what the manufacturer is claiming. This sample we pulled, there's some, and what this means for you as a company that distributes light bulbs is maybe you might have to be we might have to go back and revise that statement and say can we actually guarantee that these last 1,520 hours on average, or do we just get a bad batch of bulbs? Do we need to test more bulbs? Like, it would obviously lead to more decisions that need to be made by that manufacturer. So, so what do we know given our conclusion? We can reject the null hypothesis and again make that claim that there's something going on with these bulbs, that they're significantly lower than the expected claim. So if we have a 95% confident interval, remember that's established by just taking 1 minus alpha. So in this case, our alpha was 0.05. We can help use this uh, to inform our conclusions even further. We take our sample statistic. In this case, would be our sample statistic would be the mean of 1493 plus or minus our confidence multiplier, which is just our standard error statistic. In this case, we're using that lower the denominator of our equation, and we're going to take 1493 plus or minus. Now we're using 2 because we're having it, we're talking about an interval, so it's going to be on both sides of this number 1493. Divide that or by 85 divided by the square root of 40. So 1493 plus or minus 2 times 13.45, 1493 plus or minus 26.9. So what we're talking about is a range of values, 1466.1 to 1519.9. And we're saying, what does this mean in terms of our confidence interval? I am 95% confident that the light bulbs have a mean life less than the manufacturer's claim because the interval is completely below the population mean. This 1519 number is kind of right on the edge, but the rest of it is below. It's below our actual population mean. So we're pretty confident that there's something going on there with our light bulbs is really the short answer. Okay, so that's it. That's the one sample t-test. We're going to come back and look at a couple of different other t-tests in our next couple of chapters. So please send questions if you have them. Otherwise, I'll see you on the other side for chapter 10. Take care. Peace.